We are in Chapter 10, Part 2, Section 10.2 is Regression. This section introduces a method for finding the equation of a straight line that best fits the points in a scatter plot of paired sample data. The best fitting straight line is called a regression line, and its equation is called the regression equation. We can use the regression equation to make predictions for the value of one of the variables given some specific value of the other variable. The regression line is also called the line of best fit, or the least squares line, is a straight line that best fits the scatter plot of the data. The regression equation, because we're dealing with linear data, linear approximations, is going to be y hat equals b naught plus b1x. Algebraically describes a regression line. The regression equation expresses a relationship between x, called the explanatory variable, or predictor variable, or independent variable, and y hat, which is called the response variable, or dependent variable. And remember that the explanatory variable is used to predict the response variable. In Algebra 1 course, you would have seen this as written as y equals mx plus b. It's the same exact thing, that slope-intercept form. And right below this, we have some steps here. And it says to find the equation of the regression line with the TI-83 or 84 calculator, we first need to check to make sure these requirements are met, which states that it's a simple random sample. The scatter plot shows an approximately linear relationship between the two variables, and then the data contains no outliers and says to remove any outliers if we have any. So the next thing we're going to do is go to Stat, input our data into L1, L2, check our numbers, and then we're going to go to Stat, Test, and then F, which is going to be Lin Reg T Test. And if you go back and look at the bottom of page 1, so at the bottom of page 1, you'll notice that we are given an equation here. It's written as y equals a plus bx. And then you'll notice that down below you are given a and b. So to write your equation, you need to substitute in those values for a and for b. The example right below says, using the bill tip data, find the best predicted tip amount for a dinner bill of $100. What tipping rule does the regression equation suggest? So the first thing that we're going to have to do is input our data, which these are our x variables and our y variables, into L1 and L2. Then once we have that inputted, we need to go to Lin Reg T Test. On your graphing calculator, you need to go to Stat, to Edit, and then enter in all the values for L1 and L2, with L1 being your bill amount and L2 being your tip amount. Once you have those all in, double check your numbers, then go to Stat, Test, go down to F, Lin Reg T Test. Make sure your X list is set to L1, Y list to L2, and frequency to 1. You should also have your alternative hypothesis set to not equals to 0. And from here, you get a lot of information. What we're interested in this problem is going to be our least squares regression line, and we need a and b in order to get that. And so a, which is negative 0.347, and b, which is 0.149, and our equation is going to be listed as y equals a plus bx. So from our calculator, we get y hat is equal to negative 0.347 plus 0.149x. And if you would like to write this a little bit more like you would have seen the equation in an algebra class, you can definitely flip around those terms and call this 0.149x minus 0.347. It doesn't matter. For my open math, it will prompt you for which one to write where. From here, it also asked for how much would we be predicting to be tipping for a $100 bill. So in order to figure that out, we need to substitute in 100 for our x, since x is our bill amount. And so y hat is going to equal negative 0.347 plus 0.149 times 100. Which works out to being 14.5 0.55 if we round 2 decimal places, since we're dealing with money. So from this scatter plot of data, these 6 different values that we have collected, and we would suggest that with a $100 bill, we would be tipping $14.55. And it does say at what rate does this regression equation suggest, and this would be talking about our slope, which is our rate. And so for this, the slope is the variable that has the x in it and is the number that's in front of x. So whichever equation that you want to look at, that would be our slope. And so our slope or rate is going to be equal to 0.149. Or if we were to round this and rewrite it as a percent, I'm going to call this 14.9%. And that would be our tipping rate. So just a tad under 15%. The example below says the table below lists overhead widths in centimeters of seals measured from photographs and the weights in kilograms of the seals based upon the studies listed there. And so you can see we have the overhead width in centimeters and the weights in kilograms. And so we have our x value and our y value for our variables. And the first thing here says to create a scatter plot of the data. You can definitely use your calculator to do this. However, most students find it easier to just do this by hand, especially since for an exam you'd be writing this down anyways. So since our x variable is overhead widths, go ahead and label that. This is in centimeters. And then weights is our y variable. And this is in kilograms. And so if you look at the weights, the values that we have are between 116 and the highest value that we have is 245. So I'm going to go ahead and count by 50s on here. So 50, 100, 150, 200, 250, 300. And then we have for our overhead widths, the smallest value that we have is 7.2, and then the largest value we have is 9.8. So I'm going to go ahead and start this at 7, and we'll say 7.58, 8.5, 9, and then 9.5, 10. So from here we have 7.2 and 116. And do the best you can on this. It's a little challenging to graph decimals and small values. The next value we have is 7.4 and 154. And then the next value we have is 9.8 and 245. The next one we have is 9.4 and 202. The next one is 8.8 and 200. And then the next one that we have is 8.4 and 191. So we have our 6 data points here representing those 6 different seals in the study. So it's our scatter plot. Make sure you have your axes labeled. Part B says find the regression equation. That regression equation that we have is going to be that y hat equals a plus bx that we get from our calculator. And then graph the regression equation on the scatter plot in part A. So from the calculator, you need to put in your values of L1 and L2. On your graphing calculator, you're going to go to Stat to edit and enter in all of the overhead widths and weights of the seals that were given to us. The next, we're going to go to Stat, Test, down to F, which is Lin Reg T test. You need to make sure you have your X list at L1, Y list to L2, frequency to 1, and alternative hypothesis set to rho does not equal 0. And then from this, we need to get the information in order to come up with our regression equation. You can also see on the app that I'm using that those data points are plotted, and you can see that line of best fit going through those data points. But in order to come up with the regression equation, we need A and B. So remember, y hat is equal to A plus bx. And so A, if we round this 3 decimal places, is going to be negative 156.879. And then B is going to round to 40.182. And so our linear equation or regression equation, our line of best fit, is going to be y hat equals A plus bx. And then from the calculator, we get y hat equals negative 156.879 plus 40.182x. And then graphing this line into our equation, it'd be that straight line. Again, do the best that you can. Part C says, what does the slope and the y-intercept of the regression line represent in the context of this problem? So the easier one to talk about is the y-intercept. And so again, within y-intercept from algebra is going to be when x is equal to 0. And so for us, that means that when the overhead width is 0 centimeters, so this would be when, because that's our x variable, so when the overhead width is 0 centimeters, and if you were to substitute an x is 0 into your equation, that regression equation that we have in part B, you would get y is equal to, which is our weight. So when the overhead width is 0 centimeters, the weight of the seal is, and so if you substitute in 0 for that x value, we get negative 156.879, and we're dealing with kilograms. And this does not make sense for this problem in the context of this problem, so we'll make a little note of that. Does not make sense. So for this problem, the next thing that we need to talk about is the slope. The slope is equal to the value that's right in front of the x, which is going to be 40.182. I'm going to go ahead and write this as a fraction, and the reason why is because normally when you deal with slope, it's written as a fraction, if you remember rise over run. And so it's the change in our y variable over the change in our x variable. And since the y variable that we have in this problem is weight, this is going to be the change in the weight over the change in the x variable, and our x variable is overhead width. And so for this, what this says is that if the overhead width changes by 1, and when we say changes, we're going to say increases since it's positive, since that is lined up with our x, our change in our x here. So we would say if overhead width increases by 1, and the units that we're measuring this in is centimeters. So if it increases by 1 centimeter, then and what we talk about next is our y variable, which is the weight, then the weight of the seal. And since it's positive, we'll say increase. Weight of the seal will increase by 40.182, and our units here are kilograms. Part D says, what is the predicted weight of a seal that has an overhead width of 9 centimeters? So in order to do this, we need to use our regression equation that we have, that line, and so we have negative 156.879 plus 40.182, and we're going to go ahead and substitute in 9 for x, and the reason why is because x is in centimeters, that's the overhead width. You get 204 and we'll round it 76, and this is going to have the units of kilograms. The next thing that we have here is called a residual, and a residual is the error value between the predicted value and the observed value. So we have an equation here, observed minus predicted, and again it's between the y values. The criteria to determine if the line of best fit describes the relation between the two variables is based upon residuals. The most popular technique for making the residuals as small as possible is the method of least squares. So for this, you can look at, there's two different examples, and you can see the residual is going to be the difference between the actual and that's observed and the predicted, and those are going to be the difference between that line, which was the line of best fit, which is what we're using to predict, and the observed values, which are those dots. And so this right here is our residuals. And you can see that's a very large residual versus the one next to it, it's a lot smaller. And so versus if you look at the residuals in the first graph, this one has larger residuals. And the second graph has smaller residuals. And so to analyze our residuals, we're going to determine whether a linear model is appropriate to describe the relationship between the variables. We're going to make what's called a residual plot. This is a scatter plot with the residuals on the vertical axes and the explanatory variable on the horizontal axes. If the residual plot shows a pattern, such as a curve, then the linear model is not appropriate. And if the residual plot shows no pattern, then we can say a linear model is appropriate. So to determine if the variable of the residuals is constant, we have what's called a constant error variance or homoscedasticity on a residual plot is if the spread of the residuals is increasing or decreasing as the explanatory variable increases. And so if you look at this, we have, for the first one, there is no relationship here that we see, no pattern that we're seeing between those residuals and also our variable. So, and then versus the next one, which is the example of the homoscedasticity, which you can see the variable gets larger, it's also spreading out. And then the third one, you can see that it's not linear, and the reason why is because there is a pattern that you can see with the curve. We are in section 10.3, prediction intervals and variation. In the previous section, we saw a method for using regression equations to find a predictive value of y, but it would be great to have a way to determine the accuracy of such prediction. So we have what's called a prediction interval and a confidence interval. So a prediction interval is a range of values used to estimate a variable, such as a predicted value of y in a regression equation. And a confidence interval is a range of values used to estimate a population parameter, such as p, mu, or sigma. And so given a fixed and known value of x naught, the predicted interval for an individual y value is going to be, so that y value, the true y value, is going to be between y hat, which is what we use to estimate, and then that plus or minus that error. So y hat minus e and y hat plus e. Deviations is a measure of difference between the observed value of a variable and some other value. Often the variable is mean, and it's a difference, meaning we subtract. And so we have total deviations, explained deviations, and unexplained deviations. And we're going to be subtracting between two different things. So the first one, total deviations, is going to be the difference between the observed and mean value of the response variable. Explained deviations is going to be the difference or the deviation between the predicted and mean value of the response variable. And then the unexplained deviations, the deviations between the observed and predicted value of the response variable. The formulas for all of these are given. They're all listed here. On the next page, we have a graph that represents these total deviations, explained deviations, and unexplained deviations. Using the formula that is given on this page, you would be using the fact that you know y, y hat, and y bar in order to calculate these different deviations. And so y is the actual observed value. Y hat is going to be the predicted one that we would get from our line of best fit. And then y bar is going to be the mean of the y values. We are given our regression line, and that regression line is going to give us our predicted values. So those predicted values will be given on that regression line. And then we have our mean, which has to be calculated, which is given, mean of y. And then we also have our observed value, which is going to be our data value here, which is our actual value. And so you can see the unexplained deviations are the difference between the actual and the estimated, which is from the predicted, or y hat. And then we have our explained, which is going to be between the predicted and the mean of those y values. And then adding those up together is our total deviations. So we also have variations, which is going to be squaring this. And so we have, is the sum of the squares of the total deviation value is going to be our total variation. Explained is going to be the sum of the squares of the explained deviation values, and unexplained likewise is also going to be the sum of the squares of the unexplained deviation values. So your total variation is going to be the sum, which is sigma, of y minus y bar squared equals, and then the explained variation is going to be the sum of y hat minus y bar squared plus the unexplained variations, which is going to be the sum of y minus y hat squared. So we also have a coefficient of determination, which is given to us on our calculator, or you can take your linear correlation coefficient and square it to get the coefficient of determination. We actually discussed this a little bit earlier in the first section. So this is denoted r squared, and this is the proportion of variation in y that is explained by the regression equation. And so another way to calculate r squared is going to be the explained variations divided by the total variations. And we can compute r squared by using the definition above, or we can square the linear correlation coefficient r. It's also given to us on our calculator. Remember, r was a value that was between -1 and 1. And told us how close of a linear approximation it is that we can use. And so we had to compare that to the critical value as one method to determine if a linear model is appropriate to be used with the data points given. And so from this we can compute r squared from the formula up above, or again with the calculator. And then if r squared is equal to 0, it says that the least squares regression line has no explanatory value. And if r squared equals 1, the least squares regression line explains 100% of the variation in the response variable. The closer r squared is to 1, the better the line describes how changes in the explanatory variable affect the value of the response variable, or the better that the fit is for that line. And so we have a graphs down below about the coefficient of determination r squared. You can see where r squared is close to 1. And then as it gets farther and farther away from 1, you can see how that scatter plot looks more spread out, and a linear model would not be the best to be using to approximate that. So the next example that we have says the table below lists overhead widths in centimeters of seals measured from photographs and the weights in kilograms of the seals, and we have the study listed there. And it says find the following. So the first one asks for the explained variations, and then we have our unexplained variations, and then indicated prediction interval, use a 99% confidence level with overhead widths of 9 centimeters. So in order to calculate our explained variation, we need to do the sum of y hat minus y bar all squared. And so in order to do this, we would have to calculate our y hat values. And we already had our line of best fit. And our line of best fit was given in a previous example, and you would have to substitute in each of those x values. And so substituting in 7.2 into our y hat equation, we get 132.43. And then substituting in 7.4 into our regression equation, we get 140.47. Likewise, for the next one, we get 236.90. The next one is 220.83. The next one is 196.72. And the last one would be 180.65. We also need to have y bar, and in order to find our y bar value, we need to add up all the y values that we have for weights, which is going to be 116, 154, 245, 202, 200, and 191, and then divide by 6. And so in doing that, we get y bar, our mean of 184.67. And so for each of these, we are going to have to take y hat, for the first one is going to be 132.43, subtract y bar, which is 184.67, and then square it. Then we add together the next one, which is going to be our y hat value, which is 140.47, minus our y bar, which is 184.67, and then square it. Likewise, we have to do this for the other 6 that we have. So we've done 2, so 4 more to go. Likewise, the unexplained variations is going to be the sum of y minus y hat, all squared. And so for this, the first value that we have for y is going to be 116 minus y hat, which is 132.43. And then square it, plus the next one, the y value that we have is 154, minus our y hat is 140.47, and then square that. And again, 2 down, 4 more to go. And so the next part on here, we're going to go ahead and skip. And this idea is very tedious. It takes a lot of time to calculate these explained variations and unexplained variations. And so we're not going to focus much on it for this semester.